So we learned about the notions of client, supplier, and also contractual relation, or just contracts. But before we can really define what an abstract data type is, we need one more concept before we can get there, which is called modularity. Let's now talk about modularity, and then combined with client, supplier, contracts, we will be able to define abstract data type. Okay, modularity. And modularity, before I actually go over a list of bullet points together with you about its definition and properties, I'd like to give you visual examples. I got 5 examples over here for you. And really ranging from what you did as a child up to what you would do as a software developer. Modularity is simply everywhere. It's not really constrained to just computer science or software engineering. Modularity is really some virtual property that you want to apply whenever possible, right? Let's now get to it. And the first example will be basically what you did as a childhood activity. I'm pretty sure if not all of you, maybe most of you actually played Legos before. So this Lego individual pieces over here versus some masterpiece you can actually build from the Lego pieces, right? So that's really the idea about modularity. What exactly? So we call that the individual pieces that you use as the building blocks. They are called the interface specification. And also the masterpiece that you can actually assemble different pieces together is called the architecture, right? Let me visualize that quickly, right? So you can think about this part over here. You can see, for example, this is one particular building block over here, right? And you can see for this building block, we actually specify its dimension and also, different dimension, the sizes. So you would know how to actually connect this one with another, right? So this is what we call interface specification. Of course, you wouldn't thinking that way when you were a child. You simply just play with them together. But the underlying idea is really universal across different examples for modularity. So this is what we call interface specification. And what about the masterpiece? You can see this masterpiece over here is really built on top, maybe hundreds or sometimes thousands of different building blocks over here. And it's called architecture or assembly. So this is basically architecture by assembly, by an assembly of building blocks. And I'm just going to write down these 2 concepts just once, because for all the other 4 examples which I'm going to talk about, they all follow the same principle, right? So let me just mention again. So we talk about interface specification of a module. You can think about this is one single basic module. This is just another module. And this is assembly of different modules. So you can build an even bigger module. Everything is a module, basically. So a module may have sub-modules inside, right? So every time you want to build something, you want to think about whether there's any other module that you can simply reuse. We'll talk about reusability of module later. Okay, interface specification of a module. Versus we talk about the architecture of the assembly of building blocks, right? So these 2 ideas at different levels. At the bottom level, we got building blocks. At the higher level, we got assembly. And the same idea is going to apply for all the 4 examples. Let's take a look quickly. And the next example I would like to talk about is the daily construction. And for those of you who maybe live on your own, or whenever you do any DIY for your furniture, you must know IKEA, right? So the interface specification for individual module will be the pieces that you can actually use, right? So every time when you unbox your purchase from IKEA, you definitely have to know about what exactly are included, and somehow you want to put them all together into some nice masterpiece over here, right? So again, we got interface specification of individual modules, and also we got the assembly of those modules. So that's just another nice example for modularity, right? Even though IKEA furniture is very different from Lego toys, but the underlying idea about modularity is really the same. That's really something I want you to see through the concrete details for the application, but I want to see the underlying principle for modularity. Right, the next one is about computer architecture. So now we're moving from daily construction into the more subject-specific example for modularity. So for those of you who are familiar with hardware, maybe from your EECS 2011 computer organizations, this example should not be very strange to you. So we talk about motherboards are built from functioning units, for example, CPUs. And you can think about each individual CPU is like a module, and the motherboard is simply just going to assemble different CPUs and different other units together, right? So you can think about this maybe the specification of the interface for individual module for a CPU. And this part over here will be the assembly of different units, right? You can have CPU, you can have maybe PCI, you can have integrated Ethernet chip, etc. Right? Got many units that's assembled together, right? Again, you want to have the notion about two different levels. At the bottom level, you got just individual, the specification of individual modules. And at the top level, you actually got the integration or the assembly of different modules together. Okay, so that will be the third example. And the fourth example is about system developments. And especially, I want to draw just for your knowledge, let's say if you want to build some nuclear shutdown system, right? You want to build a shutdown system that can shut down the nuclear power plants whenever, for example, if the condition is critical. In that case, how can you actually build different function blocks, right? Let's talk about one example here. And let's say we want to build some basic units called limits alarm. So limits alarm, don't worry too much about the specific detail, but just get the idea. The limits alarm basically is going to take different inputs on the left-hand side, and they're going to have different outputs on the right-hand side. For example, you can think about here, the H over here is more like a high. It's more like an upper bound, let's say for temperature. So limits alarm can be applied to maybe temperature, can be applied to other like a physical observation you might have, from the nuclear power plant. But in this case, let's say H will be for the upper bound, and L will be for the lower bound. And also X will be the actual observation, for example, temperature, right? You want to make sure the temperature should be in between the lower bound and also the upper bound. If it is not, then you may have to set some output maybe to be maybe true, so that you will trip the system, right? That's I think that's enough for you to know. And also EPS stands for epsilon. And the epsilon idea is really about just make sure you have some tolerance for the physical observation, right? It can be, for example, your temperature can be within maybe certain like a 0.5 or 0.6 range for tolerance, within the upper bound or lower bound, right? Anyway, so that's about individual specification, and you can see more actually description over here, like an interface specification. And then, so that's more like a visual specification for the limits alarm. You can take a look just for your knowledge. If you want to discuss even further about this diagram, reach out to me. I'll be more than happy to discuss. But for the general knowledge, what I said was enough, right? So far, it's just about the specification for the individual module. In this case, the module is limits alarm, right? And when we do the specification, how exactly you actually implement this limits alarm is not important, right? We're just observing as a client to see how to use the limits alarm function block. And what about assembly? So here we actually got two assemblies together over here. So we got, so here we basically talk about how we can implement the limits alarm over here, right? When you only look at this part over here about the limits alarm, you don't care about its implementation. But now to talk about how to implement this as a supplier, let's now take off the client's hat. Let's now wear the supplier's hat. So now to really implement the limits alarm, we can do some composition of the modules. So we got one thing called hysteresis. For those of you who actually took some course in control system, if you have, you will know what hysteresis is. But for now, let's not worry. Just some function blocks. Think about in order to really build the limits alarm. To build this, you can make it as a composition of two hysteresis block, right? So we got two modules being assembled together. They got individual input and also they got final output over here, right? That's just an idea over here. And let me just go to that particular diagram over here. I just want to draw one more notes over here. Think about, yeah, this part over here is about the specification. Specification of the module versus you can think about this is the assembly, right? You can see you got one module over here. Okay, let's see if I can do better. This is one module and this is just another module, and we are trying to assemble them together so that you can see we got inputs, and also inputs over here, and also we got outputs, and outputs. With the assembly of these two modules, we will be able to implement it for the limits alarm, right? That's the idea. You can think about the assembly. The assembly as a composition of well-specified module. Right? Think about this might be module number 1, this might be module number 2. And together you can build a even larger module. Right? You can think about overall the blue one I'm boxing over here. So this is really another module. A bigger module. Right? Like what I said before. It's actually very often for bigger module to really consist of different component modules which will work together to make sure this will work as expected, right? That's really the composition idea you want to have as well. All right, so the final example I would like to talk about is so relevant to you as a software developer, okay? And the software systems are composed of well-specified classes, especially we talk about OOP. And this is just one example, so-called architectural diagram or software design diagram. You don't need to worry too much about the details. I just want to point out to you what can be relevant to what you learned earlier in the Java course so that you have an idea. You will be expected to draw a diagram like this, maybe in your EECS2011, the software design course. For this course, it's only for your knowledge, but you should at least know about when you build your software system, modularity should be the case, rather than having a single so-called Superman module in the diagram. Okay, let me just point out some important stuff to you, and then we can move on. Okay, you can think about, for example, over here, let's say this. This is a module, right? And also, this is just another module, right? Either each oval shape, each oval and each rectangle is simply just module, individual module. Individual modules. And how do we actually assemble these modules together? So there are 3 possible ways. And remember what you learned in the earlier OOP course. We can either relate 2 classes by either inheritance, aggregation for sharing, or composition without any sharing, right? So these are exactly the 3 different ways we can relate the modules together in OOP, right? So for example, one example could be, so this one over here is one way to relate these 2 classes. Maybe it's for aggregation. Aggregation. I don't have any example for composition in this case, but that's okay. But you get the idea. And also here, we also got another way to relate the 2 classes. For example, over here, this arrow over here usually show between bottom and top. So that'll be inheritance. Okay, let me just summarize quickly. So in OOP, we can assemble classes via, okay, and so these 3 things are not new to you. That's something you already learned from the earlier course. Number 1 is aggregation for sharing. Number 2, compositions. And number 3, inheritance. All right, let me now highlight it. Aggregation, composition, and also inheritance, right? That's how you assemble different classes together. And the overall, we said it's an architectural diagram. architectural diagram. Right? As part of your software documentation, you should really explain about what the architecture is, how you assemble different modules together in your projects, right? And you should not be too surprised that when you get onto not even realistic, even the medium size projects, it's not too surprising to have more than dozens of classes together, or even reaches maybe 50 or even close to 100. And so that's why it's so important to really explain to your clients or explain to your co-workers about what the architecture is for your design. All right, so enough about the example. We got 5 different examples. Hopefully now you can see really the idea about modules and also assembly of modules. Let's now try to define the design principle of modularity, right? So this will be summarizing what we have seen visually so far. Let's now go over that. Modularity simply refers to a sound quality of your design. Exactly how? Let's take a look. So there are 3 components for modularity. You can think about these are the different steps you have to take in order to reach modularity. Number 1, you want to divide. You're given some complex problem to really solve. You want to divide your big problem. You cannot really solve the big problem directly at one go, right? You want to subdivide them into different sub-problems. Individually, they will be small enough for you to solve. So you're going to divide them into interrelated sub-problems, right? It's actually, that's called the divide and conquer strategy, if you have heard about it before. And you want to, and whatever division strategy you use to go from the original problem into the sub-problems, of course, you want to make sure they are logical and they are justifiable. That's not really something we will do in this course so much, because we are still mainly focusing on implementation. But once you get to the more senior software design course, you have to know about how to justify the so-called functional decomposition of your problem into sub-problems. That's something I'll leave to your future professor to cover. And for example, let's say you're trying to design a computer game, large game, let's say, and you want to solve the problem by dividing the problem itself into sub-problem number 1. What would be the rule of the game? How exactly would the player play with each other? Number 2, what about the characterization for the actor? What would be the specification for each individual actor, right? It's a different sub-problem. And number 3 will be, how exactly do you present the game to the end user? Do you want to present it using a web browser? Do you want to maybe present it using some game console or etc., right? So these are the different sub-problems you may have. Right. The second step is about once we got individual sub-problems decomposed from the original big problem, we want to specify the solution to each of the sub-problem. So that's why I call sub-solution. And the sub-solution should be a module, right? You can think about the module over here. Let me just remind you, module can be like a single class over here, right? It can be a module, or the module can be just a single function block over here. Module can also be a single CPU, right? So that's really the idea about module. A module is only for a single sub-problem. But eventually, if you really want to get a solution for the ultimate big problem, you have to combine the sub-solutions together. Okay, it's really important to keep this in mind. Okay, let's now move on. So once you specify for individual sub-problems, and of course you want to make sure each module is really has a clear interface. You want to know exactly what the input is and what the output is. I want to connect this to what does it really mean for a computational problem to be well specified, right? Remember, we talked about this in the very beginning of the semester. A computational problem will be well specified if you know exactly, number 1, what the inputs are, number 2, what the outputs are, number 3, what the relationship is between the input and output, right? So these are the 3 ingredients for a module to be well specified, just like how a problem can be well specified. And I would like to, for your knowledge, for those of you who may have taken for 2031, EECS 2031, so you learned about the Unix operating system. You may have heard about this. There's a principle over there. Each command does one thing and does it well. For example, if you compare the command, let's say pwd, which will give you the current directory, versus the command ls, right? In that case, it will be just listing the contents. So you can see individually these commands do something different. However, you can combine them or to assemble them to do something that's bigger, right? So that's really the Unix principle you can connect to. But in the case of the object-oriented design, which is relevant to this course, each class should really serve as a module, right? So in our context, we say each class should really be solving some sub-problem. So if you want to solve a bigger problem, you want to combine different classes together using inheritance, aggregation, or composition. The final step will be to concur, which is to really combine all the sub-solution together. We're going to concur the original problem by assembling the sub-solution, right? Each of the sub-solution is really solving some sub-problem that was decomposed functionally from the original one, right? And so we talk about client supplier, which can be aggregation or composition. At the design level, whenever you got aggregation composition, remember we got client class versus supplier class. So that's why we also say client supplier relation and also inheritance, right? And so here, client supplier relation, I want you to recall whenever you got any method call, right, where you want to use some service, some method, which class will be the client and which class will be the supplier. That's why I talk about client-supplier relation before I talk about modularity, right? There's a logical order over here. And we talk about modularity, which is some virtue we would like to achieve, but what does it really mean when your design is modular? Modular simply means you satisfy the criteria of modularity. As easy as that. Of course, you need to understand what modularity really is before you can justify whether or not your design is modular, right? It's straightforward. And so there are several properties for modularity. Number one, it should be maintainable, meaning that whenever you want to fix any issues, you don't really need to fix the entire system. You can only you can really try to pinpoint exactly which module is causing the issue. You can fix that one only, right? By changing the relevant modules, right? For example, let's say this is my system, which is completely modular. And let's say I got some bugs or some issues when I run the system. And after some rigorous debugging process, I identify this class or this module specifically is the module to be fixed. So I can only attempt to fix this particular module and test it. I don't need to worry about the rest of the system, right? I don't need to worry about it because they're working well. I only need to worry about fixing the module that's causing the problem. If every time you fix an issue, you have to, it turns out you have to fix everything in your project, that means your design is not modular, right? Whenever there's an issue to be fixed, it should really impact the minimum number of modules to be fixed, typically just one. That's what I meant by maintainable. And what about extensible? It's kind of similar. Let's say if I want to introduce some new functionality, I shouldn't really need to put that functionality in here, in here, in here, and here. I don't really have to. What I can do is I can simply create another module over here. Right, let me just write it, put it down. It could be just a new module over here. So this can be just a new module. And this new module here should really reflect or encode the function, the desired added functionality I want. In that case, after I have done this, I should really try to relate this particular class into the existing assembly. For example, I can simply make some inheritance relation. I can say this class should be maybe also a subclass of this particular class over here, sorted ADT, right? I can also do that, just as an example. So that's what I meant by extensible. So whenever you want to introduce new functionality, you just add new modules. And also reusable, meaning that if I want to implement, let's say, this particular module, let's say I want to, and there is certain functionality which I believe is already, which has been already implemented by maybe this module already. In that case, I don't really have to reinvent the wheel from scratch. All I can do is I can simply directly reuse this module here, and by calling the method. So this will be the clients, and this will be the supplier, right? So no duplicates will be needed. That's what I meant by reusable. So a module may just be used in different composition, right? So for example, this module over here can be used by this particular module this module here can also be used by this particular module, like a helper method idea. Okay, you can think about helper method itself is also like a mini module in some way. Right, so what would be the opposite to modularity? So this is something I call this, not just I call, many people call the Superman module. A Superman module would be something like this. Rather than having so many individual modules and try to assemble them together, you have a single Superman module like this, only a single module. You put everything you want to do over here, right? It's a very typical mistake that people actually do, because in that way they thought it's really convenient. I just have a single class rather than having 100 classes. And in that particular single class, I'll put everything that's needed for me to implement in there. However, as you will learn about maybe in your senior level design course, having a Superman module is highly discouraged. You definitely shouldn't really do a Superman module. That will simply make extension, fixes, or maintenance very difficult to actually achieve, right? You want to avoid that. Right, so Superman module or Superman class is really something you would like to avoid. You definitely want to divide your solution into different sub-modules that are interconnected together.